All right, so let's talk about the periodic table. We're going to be talking about periodic table and some patterns that we see in it, okay? So the key thing to remember in this unit, and I guess going forward too, is thinking about mostly the valence electron, okay? The valence electrons are the interesting ones because those are the ones that really determine the atom's characteristics and properties. Okay, and we learned about valence. It's the outermost electrons. And when an atom becomes an ion, whether positive or negative, you either lose or gain electrons in the outermost shell. Okay. Okay, so I want you guys just to kind of refresh your memory, just make sure that we're all have the same idea about valence electrons. I want you guys to, for each of these elements, write down how many total electrons they have, and also how many valence electrons they have. Okay, so how many electrons do they have in total? And how many electrons do they have in the outermost shell? So I'll give you guys about 2 minutes to try it out, and then we'll see if you guys got the right answer. Okay, so let's start with potassium. Potassium, very easy. How many total electrons? 19. 19 total electrons. And how many valence? 1. So 19 electrons and 1 valence electron. Helium, there's going to be 2 total electrons and 2 valence electrons, okay? Chlorine is going to be 17 electrons total, and it's going to have 7 valence electrons. Good? Okay. Potassium, or the ion, is going to get a little bit trickier, but you're going to have 18 total valence electrons, and you're going to have 8 valence electrons. Oh, my bad. Yeah, 18 electrons. Okay, and then 8 valence electrons. Another mistake? Oh my gosh, guys. Damn. All right, dude. Just watch how I grade your guys' test this time. Yes. Yeah, so regular potassium has 19 protons, right? And so regular potassium has 19 electrons, but if it has a +1 charge, it means it lost 1 electron. So it'd be 18 electrons. 8 valence because that's the electrons in the outermost shell. But K+ loses the 4th shell, and it has only 3 shells, and the third shell is filled up. Yeah, these are good questions. Okay, let's go to sulfur now. Sulfur 2-, sulfur's ion is going to have 18 total electrons, and it's going to have 8 valence electrons. Okay, and then Cl- the chloride ion, is also going to have 18 electrons and 8 valence electrons. Okay, so if we drew the Lewis structure for these guys, they would look pretty much the same. Everyone good with that? Okay, so we're going to move on now. We're going to be talking about something called effective nuclear charge, okay? And what is it? The variable, we write it as ZEFF, Zeph. Okay, and Zeph, it basically tells you how strong an electron is connected to the atom, okay? So the higher the Zeph, the more tightly the electron is held. The lower the Zeph, the less it's held. Okay. The more tightly it's held. Effective. Effective nuclear charge. Quite a mouthful. Okay. Now, the way that we think about Zeph is there are 2 things that matter. Okay, so we have an example of an atom right here. Okay, we know that the nucleus of an atom is positively charged, right? Because it's made out of protons. Okay, we know that electrons are negatively charged. And so this is where the little, I guess, balancing game comes in. So let's say the nucleus and this electron. What kind of force do they feel? Do they attract or repel? Attract, right? So the electron wants to get closer to this good-looking nucleus, right? It's like an amazingly good-looking girl, okay? All the thirsty guys swarm around her. Okay, but as this electron wants to get closer to the good-looking lady, what's going to happen? There's other electrons that are also attracted, right? And so what are those electrons going to do to each other? Yeah, they're gonna fight. They're gonna push each other away. And so this is where the Zeph comes in. You guys laughing. I'm not talking about you guys. And now I want to know too, but I don't really care. Anyway. So, okay, but that's basically why there is an effective nuclear charge, because every electron is going to feel the attraction towards the nucleus, but it's also going to feel the repulsion of the other electrons that are in the way, okay? So, you know, the ones that are closer to the nucleus in the first shell, they're going to be obviously more attracted to, they're going to feel a stronger Zeph, a stronger attraction. These are like the two guys that the girl kind of keeps close. You know, she goes to class with them, she DMs them, texts them. And then the ones that are far away are kind of just like the, hey, can I borrow your homework kind of relationship. Okay. So a less effective nuclear charge. Okay. See, this is why they call it chemistry. Okay. Helps understand.
How come they never, like, how come the protons never, like the protons never touch the electrons on the outside?
Because of the electron repulsion. The electrons repel each other.
No. I'm thinking about like the innermost ones. Why would they never? They don't really touch the nucleus.
The protons?
No.
The electrons?
The nucleus is made out of protons.
Protons, yes.
And the electrons that are circling around, how come they never touch the protons in the middle?
Because the electrons, other electrons repel each other.
Okay.
Because remember, they're not stationary. It's not like they're gonna stick on one side. They're constantly moving around. Yeah, and so they're not going to be able to. Yeah. Okay, so the way that we calculate Zeph is we need to subtract the number of protons, okay, which is Z. So proton will be constant for every single element. And then we're gonna subtract S, which is the electron repulsion, or it's called the screening constant, okay? But there's a very easy way to calculate the S, okay? You can kind of see an example right here. Okay, the screening constant, the way that we calculate S is right here. It's just going to be the number of inner electrons, the core electrons. Okay. So if this is the example right here, we got an example with we got an atom with 15 protons. So the nuclear charge Z is 15. Okay. And then the S value is going to be the inner electron. So basically not valence, okay? Okay, and if you look in the first shell, there are 2 in the first shell. There are 8 in the second shell. And this is going to be S. And that's going to be how you calculate that. Yes.
Oh,
whichever one wants to go first.
So it's all the ones that are inside self-there.
Yeah. Usually we're talking about the Zeph. We're calculating Zeph for the valence electrons, and that's what we use that for. Yeah. Yeah. If we're talking about atoms with 3 shells. If we're talking about atoms with 2 shells, then we would only count the 2 in the first shell. Yeah. It's basically anything that's not valence. Okay. Which kind of leads into the first practice problem. I want you guys to calculate the Zeph for carbon and sodium's valence electrons. Okay. Carbon and sodium. Yeah, and Zeph is for valence electrons. All right, guys, so let's calculate it for carbon and sodium's valence electrons. So we just got to use this equation right here. Zeph is C minus S. So let's do it for carbon. So the Zeph for carbon, we're going to start with the protons. How many protons does carbon have? 6. Okay, and if you take a look at carbon on the periodic table, it has 2 shells, right? So how many inner electrons do we have? 2. Okay, because carbon, if we draw the shell model, will have 2 shells. It'll have 2 electrons in the first shell, 4 on the outside shell. And so each one of those valence electrons will be shielded by those 2 inner electrons. So each of them are going to have a Zeph of 4. Okay. Okay. All right, let's go to the Zeph for sodium, okay, how many protons does sodium have? 11. Sodium has 3 shells, and so it's going to be shielded by the 2 inner shells. So we're going to subtract 2 from the first shell, 8 from the second shell, and so that's going to give us a Zeph of 1. Okay. So which electrons are more attracted to the atom? Carbon's valence electrons or sodium's valence electrons? Yeah, carbon, these guys are more attracted or held more tightly, and that makes sense, right? Because carbon only has 2 shells, whereas sodium is going to have 3 shells, so they're further away, so they'll be less attracted. Okay, yeah. Copper, yeah. So if we were taking a look at copper, hold on. Can I erase this? Yeah, okay. So if we're taking a look at copper's Zeph is going to be the number of protons. So we got 29, and we need to subtract the inner shell electron. Okay, so if you take a look at copper is going to have, hold on, count. It's going to be 4s2, and then 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 3d9, right? And so for this one, we would have to just subtract anything that's above this outer shell. This would be the outermost energy level. So anything underneath that. So we would subtract 18. Okay. But we also need to keep in mind that this is in the third shell, right? Because this is 3. So this is the shell. Even though it's in the D subshell, because it's part of the third shell, we have to subtract the 9 that's from the third subshell. So we do, what is that, 27? So the Zeph will be 2. Okay. But very rarely will we be looking at transition metals for this. Yeah, and so this is where it gets a little bit tricky with the subshells, because D subshells are technically part of the third shell, even though they're in the 4th row. Okay. And that's why earlier I think I liked to write it like this. This is probably why I learned it like this. Okay, it's probably so that we know that this is part of the inner shells, not the outer shell. Okay. Okay, ready to move on? Okay, next one is very simple. We've actually learned it already, and it's the most common ion. It's the ion that the atom wants to become. Okay. So atoms, they don't like having incomplete shells. So let's look at good example. Let's look at fluorine. So if we take a look at fluorine, fluorine has 7 valence electrons, right? Okay. But how many electrons fit in that valence shell maximum? Yeah, it can hold 8. So the second shell can hold 8. Okay. So fluorine has 7 electrons in the valence shell, but the second shell can hold 8, which means it's not happy. It's unstable. Okay. It's not where it wants to be. And so what atoms do is they either try to empty or fill up their outermost shells with electrons in order to become an ion. Basically, whatever is easier. And we learned this, right? The pattern on the periodic table. We said that the first column, everybody wants to become +1, +2, +3, -4. We learned this pattern, right? Okay. So this is basically the same thing. But now we're going to be learning why or how they become these most common ions. Okay. And these guys have no most common ion. Okay. All right. So in order to do that, we're going to be taking a look at shell models. And so the easiest way to draw the shell model of an MCI, we're not going to do many problems with this just because it's kind of redundant. But the way that we want to figure out what the most common ion is we're going to draw the shell model of the neutral atom, figure out if it's easier to fill it up, the outside shell, or empty it, and then we're going to calculate the charge. Okay, so we'll do sodium together, and then I'll have you guys try oxygen on your own, and then after that, we'll move on. This isn't, I don't want to spend too much time on this. Okay, so sodium. So we're going to draw regular sodium, the shell model. How many shells does sodium have? 3. So we're going to do 1, 2, and 3. Okay, let's fill in all the electrons. You got 2 electrons in the first shell, 8 in the second shell, and 1 in the valence shell. Okay. Now, if you take a look at this sodium atom, it has 1 valence electron. Okay, but how many electrons can go in the third shell? Yeah, it can hold 8. Okay. So sodium is unstable because it has an incomplete valence shell. And so what it's going to do is it's either going to try to gain electrons or lose electrons to fill up the outer shell. So it can either get a shell by gaining 7, or it can just lose 1 electron. Okay, and just if you just look at the numbers, it's easier to lose 1 electron, right? So what sodium is going to do is get rid of this electron out here. This shell is empty. And then so that becomes a new valence shell. And if you take a look at this valence shell, it's filled with 8 electrons. And so this guy is happy now. So that's the reason why sodium in the first column wants to become +1. It's because it wants to get rid of that electron in the valence shell. They're not going to ask you a question on this. No. This is just here to build to a point. We're going to get to it.
Does it lose energy when it loses
Lose energy? What loses energy?
like does it release energy whenever
When it releases the electron, yeah. Okay. Easy peasy. Okay. Let's do oxygen. Actually, we'll do it together and we'll move on together. So oxygen is going to have 2 shells. So 1, 2. And then it is going to have 6 valence electrons. 1, 2, 3, 4, 5, 6. Okay. The valence shell can hold 8 max. So the options that we have are it can either gain 2 or it can lose 6. Okay. So again, look at the numbers. It's easier probably to gain 2. So oxygen is going to gain 2 valence electrons. If it gains 2 electrons, it becomes more negative. And so that's why oxygen wants to become 2-. And this is the reason behind the most common ions, why they have the values that they do. Okay.
where is it gaining the electrons from?
From a different element. Yeah, it's through a reaction. Yeah. Yeah, and then so it's gonna go -4. So the carbon row is the one that you gotta know it likes to become -4, and then the last column is already complete, so they have no ion. That's why they're inert. Okay. All right, we chilling? Okay. All right, let's go over the last thing for today, and then we'll wrap it up with that. Okay. Okay. So we are going to be looking at, and this is the trick, the +1, +2 thing. We're gonna be looking at something called electronegativity. Okay. And electronegativity is basically how tightly an element holds onto its electrons. Basically, how greedy is it? How much does it not want to give away electrons? Basically, how hard is it to steal an electron from this element? Now, there are 3 factors that you want to look at, and they go in order of importance, okay? So the most important thing is, what is the most common ion? Does it want to gain or lose? Okay, because if it wants to gain an electron, it's going to be very difficult to take an electron from it, right? When it's trying to gain more. Okay, whereas if it wants to lose an electron, it's probably pretty easy to steal from it, right? So if you guys want to, let me just kind of put qualifiers on this. Go for the MCI. If it wants to gain electrons, that means it's going to be it's going to increase the electronegativity. But if it wants to lose electrons, it's going to decrease the electronegativity. Okay. All right, the thing that matters next, importantly, are the number of shells. Okay, the distance from the nucleus. Okay. Because if the electrons are far from the nucleus, it's going to be easy to steal the electrons, right? So that means if it's easy to steal the electrons, that means the electronegativity is going to go down. But if the electrons are very, very close to the nucleus, it's going to be hard to steal the electrons, so the electronegativity will go up. And then lastly, it's going to be the number of protons. Okay. Because the protons are, if you have more protons in the middle, right, there's a greater positive charge that's going to attract the electrons more. Okay, so if there are more protons, that's going to increase the electronegativity. And if there are less protons, it's going to decrease the electronegativity. Because the more protons there are, the more positive energy there is in the middle. So the more it will be able to pull the electrons. But again, these go in order of importance. You care mostly about MCI. If the MCIs are like equal, then you look at the number of shells. The number of shells are equal, then you go to the protons, and the protons will be the last determining factor. But that's the least important out of the three. Okay, and then we will finish up these practice problems, and then we will be done for today, okay? Okay, so I'll go over one of them with you, and then after that, I will have you guys try the other ones on your own, okay? Okay, so let's take a look at sodium and lithium, and we're trying to figure out which one is more electronegative. Now, the first thing you want to look at is the MCI. So if you take a look at sodium, what is sodium's MCI? Yeah, Na+. What is lithium's MCI? Yeah, Li+. They're both in the first column, so it's just positive. So they have the same MCI, so that doesn't really help us, right? So we go on to the second one. Number of shells. How many shells does sodium have? 3. Okay. And how many does lithium have? 2. Okay, so what this tells us is that lithium's valence electrons are closer to the nucleus than for the sodium, right? Because sodium's valence electrons are 3 shells away, whereas lithium is only 2 shells away. So which one do you think holds the electrons more tightly? Yeah, lithium. This one is going to be more electronegative because the valence electrons are closer to the middle. Right? Like if you're trying to steal my phone, if my phone is very close to me, it's harder to steal my phone, right? Because it's closer. But if my phone was over there, it's a lot easier to steal my phone because it's further away from me. Okay, same concept. The further something is away from the center, the easier it will be to take, the less electronegative. Okay. That's true. It is pretty crazy. Okay. I'm gonna give you guys maybe about 2 minutes to try out B and C, and then after that, I'm gonna show you guys a trick that will help you do this a lot more easily. Okay. I could have, but I'm trying to make a point here. Okay, so let's go over part B. So part B, we're comparing fluorine and beryllium. So if we take a look at their MCIs, or we can just talk about gain or lose. Does fluorine want to gain or lose electrons? Gain. And what about beryllium? Yeah, so we got one guy that's trying to give electrons away, and we got one guy trying to get more electrons. Okay, which one do you think will be more electronegative? Yeah, the guy that wants to gain, so fluorine will be more electronegative. Okay, because fluorine is trying to get more electrons, right? If it's trying to hoard more electrons, obviously it's going to be hard to steal what it already has. Okay, because it wants more. Whereas beryllium is trying to give it away, and so it'll be very easy to take electrons from beryllium. Okay? Yes. No, beryllium's trying to lose because beryllium wants to become Be2 plus. It's a positive charge, which means it loses. All right, let's go to the next one. We got nitrogen and sulfur. Now both of these guys want to gain electrons, right? Okay, nitrogen wants to gain and sulfur wants to gain. We can talk about the charge if you want. Like nitrogen is 3 minus, sulfur is 2 minus, but that's going to complicate things and it actually gets addressed in these other two steps. So we'll ignore that for now. They both want to gain. How many shells does nitrogen have? 2. Okay, and how many shells does sulfur have? Okay, so pretty easy here. Which one is more electronegative? Yeah, nitrogen. Okay. You guys ready for me to show you guys the trick?
Yeah.
Okay. So you still need to know how to do this because there are some times where the trick will not work very well. But let me show you guys the trick on the periodic table. Okay, the trend for electronegativity is going to be what color should I? I'll do black because I don't see black here. As you go up and as you go to the right, it's going to get more. Whoa, that's quick. More electronegative. Okay. All right. So thank you for today, guys. I'll have this recording posted. And yeah, let me know if you have any questions. I'll see you guys on Monday.